Today we're going to talk about expected value. Look at the problem that's been given, or the situation. A player pays you $5 and draws a card from a deck. If he draws the ace of hearts, you pay him $100. For any other ace, you pay $10. And for any other heart, you pay $5. We're going to break this problem down, and we're going to use a table to determine the expected value and also something known as the standard deviation. And I'll explain more as I go on. When we go to make up this table, we're going to be looking at, first of all, what are the possible outcomes, and then we'll consider what is our random variable. And we'll also consider the probability. And let's see here. Then of course we'll get to expected value. Now let's go ahead and take a look at some of these concepts right now. First, let's go ahead and fill in this row of possible outcomes. So one of the outcomes that we'll see here is the possibility that we win $100. That occurs when we draw an ace of hearts. So let's say that an ace of heart is drawn. So ace of hearts. There we go. And if that happens, you win $100. Now, in that case, the random variable, which we're going to call x, by the way, our random variable is x. In that case, what happens is the random variable is going to stand for winnings, and our winnings in this case would be $95. Go ahead and put a $sign in there. There we go. And then let's take a look at another possibility. It's also possible that something else could happen. Let's see here. You pay $5, and if you draw the ace of hearts, you get 100. For any other ace, $10. So any other ace. And in the case where any other ace is drawn, you will win $10. Now you paid $5 to participate, so your winnings in this case would be $5. The value of the random variable x, the winnings, would be $5. Another possibility is that you could get any other heart. And so if that happens, any other heart, then you, let's see, for any heart, the $5 is paid out. So you bet $5, you get paid $5 back, so the winnings would be 0. And for any other card, any other result, you win nothing. Sorry. Or he who is playing wins nothing. Makes us feel less bad. So if there was nothing won, then $5 was paid, so the winnings would be negative $5. There we go. So now we can see all the different values of the random variable x. X could be 95, or 5, or 0, or negative 5. Now let's take a look at the probabilities here. What's the probability of drawing an ace of hearts? I'm going to let you pause the video for a moment and think about it, and if you can fill in the probability, that would be fantastic. In the meantime, I'm going to go ahead and remind myself this is abbreviated as P of x, and we'll be using that notation very soon. Okay, hopefully you're back and you figured out ace of hearts. The probability of getting that is 1 out of 52. And what about any other ace? What's the probability of getting any other ace? Again, if you could pause the video and you can fill in this block, that would be great. I believe the probability of getting any other ace is 3 out of 52. And then any other heart, pause the video and see if you can fill this in. I believe the probability of getting any other heart, let's see, there was already one possible heart that we would have gotten a prize for, so any other heart would mean 12 out of the 13, and that's 12 cards out of 52. That's the probability. And then winning nothing would be any card other than these, and that would make 36 possible cards out of 52. Now, the next thing is, now that we've got these probabilities, oh, by the way, let me make sure that I say this really quickly here, is that there's something that's important about these probabilities. When I look at these probabilities together, there's something that's important about the sum of these probabilities. I'll write sigma for sum. The sum of all the probabilities should be equal to 1. That statement, what goes along with it is the idea that you only have a valid probability model, and that's what this is, a probability model. You only have a valid probability model if all the probabilities add up to 1. So in this case, when I look at all my possible outcomes, all the probabilities of them better add up to 1. That is something that's very important. Again, the idea is you only have a valid probability model if all these add up to 1. Now finally, let's get to the good stuff here. Let's calculate the expected value. The expected value, E of x, is also, we can also refer to it as mu of x. That's the Greek letter mu. Now, why do we look at it in that way? Because the expected value in certain respects is the average of something. And I'm going to go ahead and off to the side, I'm going to write out the formula for what expected value is. Expected value is the sum of every individual value of every random variable times the probability of that random variable occurring. If I multiply the value of the random variable times the probability that it could occur, and then I do that again and again and again, and then I add all the results together, I will get the overall expected value. And that's also known as the mean, and that's why we refer to it as mu of x. So let's get cooking here. Let's go ahead and do some math. So we'll do 95 times 1 over 52. And if you pause this video, I'll let you go ahead and fill in the rest. Okay, so this is what you should have in the rest of your table. Now, what you should do is multiply, 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 and then add all these together. So you'll add whatever the product of this is, plus the product of this, plus the product of this, plus the product of this, for one big sum. And go ahead and pause the video and do that calculation, and in a moment I'll tell you what that sum should be. So if you did your math correctly, you should have gotten approximately negative 1.34. And before I go on and say anything more, I'd like you to take a moment and think to yourself, what does that negative 1.34 mean? It's kind of important that you understand what the meaning of this number is, aside from just being able to make the calculation and get it. Go ahead and pause the video, look over the problem, and see if you can figure out what the negative 1.34 means. All right, I'm hopeful that you came to the conclusion that the negative 1.34, That is the number of dollars that you can expect to win on average when playing this game many, many times. There's a lot of stuff that comes into play when studying expected value. One of the things is the law of large numbers. The law of large numbers says that if you do something enough times, then the result that you expect to get should match the theoretical calculation. And in this case, we did a theoretical calculation. So if we played this game many, many times, we would expect on average to lose $1.34. Now, when you look at the law of averages, what does many, many times mean? Well, it means infinitely many. So that's a lot of times. Even so, it gives us an idea that if you go to play a game designed like this, you can have the expectation that you will lose. That's an important concept to realize from this result right here. Okay, is that in certain situations, if you can calculate what you're going to put in and what you can get out, it's kind of nice to know up front, is it possible will you usually win or will you usually lose? Now, we're going to get a little bit more information to help us make any decision by looking at the variance and the standard deviation. But having this expected value, or this mean, this average value that we can expect to get when playing this game, it's very important.